Okay, let's unpack this. We're diving deep today into the source material on just a giant in the field, James Gosling.
Yeah, an absolute architect of modern computing.
Right. And if you've ever, I don't know, run an enterprise application, loaded a web page back in the late 90s, or even used an Android phone, his work has touched your life.
Definitely. He gets this title, the father of Java, which is true, of
It's
course.
deserved, yeah.
But our sources really show that it barely scratches the surface of his actual influence.
That's what we want to get into.
Mm.
The sources stitch together this amazing narrative, right? It covers decades of innovation. It tracks him from his roots in Canada to Sun Microsystems.
And then Oracle, Google, and finally to AWS, right up until his retirement, which was just a few months ago in July 2024.
So this isn't just a biography. It's really, I think, a lens into the history of modern computer architecture
It
itself.
really is.
Our mission today is for you, the learner. We want to give you that critical shortcut to understanding Gosling's unique path. We're going to trace that specific intellectual journey, from these surprisingly complex high school projects.
All the way to this philosophy of code independence that led to the famous write once, run anywhere paradigm.
Exactly. How did a student's project, this need for academic portability, eventually somehow morph into the infrastructure that powers global commerce? That's what we need to figure out.
We're looking at a true foundational architect. He's a Canadian computer scientist born in Calgary, May 19th, 1955. And
Well,
he profoundly shaped how programs get distributed and executed on all kinds of different hardware.
yeah, his early work really defined the philosophy that let the internet and later cloud computing scale the way they did. So let's start at the very beginning. Calgary, Alberta.
Right. The sources mention his background, English, Welsh, Scottish, Icelandic descent. But what's really fascinating is how early he was thrown into designing real high-stakes systems.
In high school, that's the part that's just mind-boggling. He's at William Amberhart High School, and while other kids are doing, I don't know, textbook problems.
He's solving problems for space physicists, not an exaggeration.
No, it's not. The sources are clear. While he's still in high school, he gets a job writing software to analyze data for the University of Calgary's physics department.
And this wasn't like some simulated data set for a class project. This was hard, raw telemetry coming straight from the ISIS-2 satellite.
Okay, wait, an ISIS-2 satellite.
Yeah.
How? How common could that have been for a high school kid in Calgary in the 1970s to be trusted with actual space data?
Almost unheard of. It just shows this incredible level of trust in his abilities from a very early age.
But more than that, it forced him to think about system robustness right out of the gate, didn't it?
It had to. The ISIS-2 satellite, which was launched by Canada in '71, was studying the ionosphere. Analyzing that kind of data it's way more than just basic coding.
What are the challenges there?
You're dealing with huge volumes of data. It's potentially noisy. It's coming in asynchronously. And it has to be processed accurately. One mistake, and you could ruin crucial scientific analysis.
So failure has real consequences.
Big ones. That early exposure to high-stakes data processing forced him to prioritize robustness and scalability from day one. It just became part of his DNA as an engineer.
And that experience clearly laid the groundwork for a whole career focused on building reliable systems. He stayed close to home for his undergraduate degree.
Yep, got his Bachelor of Science from the University of Calgary. But then he follows that classic path for anyone wanting to do advanced research. He moves to Carnegie Mellon University, CMU.
Right, for his MA and his PhD in computer science.
And CMU at that time was, it still is, but it was just this hotbed of computing innovation. His time there was focused on theory, sure, but he also produced these really practical tools that show he was both a builder and a thinker.
Let's talk about the first one, which is really about developer tools. It's something coders would know.
Yes, while he was working on his doctorate, he wrote his own version of the famous text editor, Emacs. He called it Gosling Emacs, or Gosmax for short.
And Emacs is not a simple program. It's one of the most foundational, extensible, complex developer tools in history.
It is. So for him to write his own robust version, it just shows this deep, deep engagement with the very process of creating software. It's like he wanted to improve the foundational environment where all the work gets done.
But then there's the other project from that time, which is maybe even more important in terms of what came later with Java. It's about system design.
This is where it gets really interesting, especially when you think about architecture, because even before he joined Sun, Gosling was dealing with concurrency and parallel computing at a level that, frankly, very few people were.
And the sources have a specific example of this.
They do. They detail how he built a multiprocessor version of Unix, specifically for a 16-way computer system that they had at CMU.
16 processors. Let's just pause on that. In the early 1980s, 16 processors all trying to cooperate on one system. That's bleeding-edge stuff.
Absolutely. It's a massive engineering challenge. You're designing an operating system kernel that has to manage all of that communication, all 16 processors talking at once.
He forces you to internalize things like concurrency, thread safety, resource synchronization.
All of it. If you're building a system to manage that kind of parallelism, you are inherently forced to think about how code behaves in these messy, nonlinear, distributed environments.
Which are the exact problems that Java, years later, was designed to solve for everyone else.
Precisely. It's that old saying, necessity is the mother of invention. A high-level theoretical side of all this work then culminated in his doctoral thesis in 1983.
And the title was Algebraic Constraints.
It sounds super academic, I know, but the core idea is central to modern software engineering. It's all about defining and managing complex relationships within a structured system. Think of constraints as just strict rules. If A happens, B must follow, or C must never happen.
So how does an abstract theory about relationships and rules actually show up in a practical language like Java?
It's everywhere in Java's design. If you look at Java, what are its defining features? It has strict type safety. It has compulsory exception handling. It has a managed memory model. These are all ways of algebraically constraining the programmer.
Right, so unlike older languages like C, which give you enough rope to hang yourself,
Java enforces rules that limit how much chaos you can introduce. His thesis on algebraic constraints is the intellectual foundation for Java's whole design philosophy. Predictable, rule-based, safe execution.
Okay, so his student career creates this perfect trifecta. You've got deep engagement with developer tools, with Emacs,
Mastery of high-level parallel systems with that 16-way Unix build.
and a theoretical foundation built on strict rule-based design from his thesis.
Yeah.
That exact skill set just seems tailor-made for a place like Sun Microsystems.
And that's exactly where he went. That trajectory led him straight to Sun Microsystems in 1984.
And he stayed there for an incredible 26 years.
26 years. I mean, that's an entire career. And in that time, he didn't just define his own career, he really defined the identity of Sun, which for so long was all about innovation in networking and open systems.
It's really important to remember, though, that before he ever got to Java, there were other huge projects. And some of them failed strategically, but were still brilliant technically.
The prime example, absolutely, is GNU-WS, the Network Extensible Window System.
What was GNU-WS trying to do?
GNU-WS was Gosling's big idea for an early Unix windowing system. And on a technical level, it was brilliant. It was based on the PostScript language.
The same language used for printing documents.
The very same, which made it incredibly powerful for rendering complex graphics and text consistently, especially across a network. It let you display applications remotely, which was a crucial feature for the distributed computing world that Sun was championing.
But technical superiority, as we see time and time again, often loses out to business strategy. And this is where it gets really interesting, because GNU-WS completely failed to become the standard.
It lost the war. It lost the war for the desktop to the X Windows system, which is still, in some ways, with us today.
So why? Why did a technically superior solution from a genius like Gosling just fizzle out?
It boils down to a classic and very costly strategic mistake. The sources are unanimous on this. It was all about licensing.
Sun kept it proprietary.
They did. Sun did not grant GNU-WS an open source license. It was a closed proprietary system, and that was a fatal miscalculation in the world of network Unix computing.
Right, because the X Windows system was managed by the X Consortium. Its license was super permissive, basically free for anyone to use, adapt, extend.
Exactly. So
Yeah.
put yourself in the shoes of a hardware vendor in the 80s. You're HP, you're DEC, you're an independent software developer. Are you going to bet your entire future on a closed system that's completely controlled by your competitor, Sun?
No way. You're going with the open consortium-governed standard that you can actually use without asking for permission or paying a fee.
And that's what everyone did. The proprietary barrier just stopped the ecosystem from ever growing.
This was a multi-million-dollar battle for the future of how we interact with networked computers. And the better engineering lost to the better licensing strategy.
It was a powerful and I'm sure very painful lesson for Gosling and for Sun's leadership. The sources strongly suggest this failure directly informed their strategy for Java a few years later.
How so?
The initial widespread availability and the permissive licensing of Java were a direct reaction to the proprietary trap that swallowed New WS. The lesson was clear. If you want to create a global standard, pervasive adoption is everything, even if it means giving up some of that initial proprietary control.
He even co-authors the New WS book in 1989, but by then the writing was on the wall.
The market had already made its decision.
Okay, that context is so vital. Now let's pivot from that very visible failure of New WS to a more obscure but maybe equally crucial little technical success. It really highlights his mastery of the low-level plumbing of systems.
You're talking about SHAR.
The bundle program, known as SHAR.
SHAR stands for Shell Archive. It's a low-level Unix utility that Gosling co-wrote. And to understand why it was so important, you have to remember what that era was like. This is before reliable tools like ZIP, before stable binary transfer protocols were everywhere.
So just sending a group of files from one Unix machine to another could be a huge pain.
A huge pain. You had all these different potentially incompatible systems. How do you get a whole directory of source code from one to another reliably?
It seems like such a mundane problem, but it's foundational. So how did SHAR solve it?
It was so simple, it was brilliant. It took a bunch of files and bundled them into a single massive shell script.
So it's not a compressed file, it's a script.
Exactly. When the person on the other end received this single file and executed it, the shell archive would just unpack itself, recreating all the original files and directories. It leveraged the one thing you could count on being compatible across every single Unix system.
The Bourne shell interpreter.
Yeah, the shell. It turned your entire package of files into a self-executing text file, which was way easier and more reliable to send through primitive email systems or early FTP. It completely avoided the nightmare of inconsistent binary formats.
It's another example of that architecture-neutral thinking, isn't it? Find the one common layer that exists everywhere and write for that.
That's a great way to put it. And the sources confirm its importance. This little utility was detailed in the absolute Bible of the field, the Unix programming environment, by Brian Kernighan and Rob Pike.
Pages 97 to 100, specifically.
If your tool makes it into that book, you've achieved a kind of permanent foundational status.
This dual capability is what's so striking. He could design a huge, complex, network-aware graphics system like New WS.
And at the same time, engineer a simple, totally robust, low-level utility like SHAR.
He understood the whole stack, from the shell script all the way up to the network graphics layer. And that duality is the perfect bedrock for building something like Java, a language that was designed to span all of those layers.
And so, now we get to the main event, the magnum opus. In 1994, James Gosling is formally credited with inventing the Java programming language.
And he was the lead designer. This all came out of an internal project at Sun called the Green Project, right? Which was originally aimed at, like, smart toasters and consumer electronics.
It was, yeah. But the true potential of the language became clear very, very quickly.
And crucially, he wasn't just the guy with the idea. He wasn't just the architect drawing blueprints. The sources confirm he did the hard work. He implemented the language's original compiler and virtual machine VM himself.
That's so critical. He owned the blueprint and the first working model. He built it.
So Java was created to solve the ultimate problem of a networked world: platform incompatibility. Software for a Sun SPARC machine wouldn't run on an Intel PC, which wouldn't run on an Apple computer.
And Java's big idea was to introduce this concept of architecture-neutral execution to just wipe that problem away.
Okay, let's break that down. What does architecture-neutral execution actually mean for a developer writing code?
It means you, the developer, you stop writing code for a specific chip. You're not targeting the Intel instruction set or the SPARC instruction set. You just write your Java source code.
And then the Java compiler takes that source code and translates it into an intermediate format.
Right, called bytecode. And this bytecode is the magic ingredient. It's not machine-specific at all. It's specific to this standardized imaginary computer that we call the Java Virtual Machine, or the JVM.
So the JVM is like a universal translator that you install on every single physical computer. The bytecode, your program, then runs exactly the same on a giant server or a little desktop.
Because it's always executing on the exact same abstract machine, the JVM.
And that is the core of the write once, run anywhere philosophy.
That's the whole game. And what makes this deep dive so fascinating is that this revolutionary idea, it wasn't a sudden flash of genius. It didn't come out of nowhere. The sources let us trace the idea back to two very specific earlier technical challenges he had faced.
These were like proofs of concept for virtualization.
Exactly. Let's start with the immediate trigger, the thing that happened at Sun that directly inspired the Java VM design.
Okay.
The idea came to him while he was working on a really tedious task, porting software from a niche piece of hardware, a PERQ computer.
A PRQ computer. Never heard of it.
Not many people have. It was a high-performance graphics workstation, but it had its own proprietary system, and Sun needed to move its software off of the PRQ and onto more standard computers.
So rewriting everything from scratch would be a nightmare.
A total nightmare. The challenge was that the PRQ had its own internal code, so Gosling's solution was essentially to build an emulator. The PERQ used this internal language called Q code.
So Q code was its machine logic.
It was its instruction set, yeah. So Gosling wrote a program that would translate that Q code into instructions for a more standard machine at the time, the VX assembler. And then on top of that, he built a layer that emulated the PERQ hardware on the new VX machine.
Wow. So he was translating and mimicking one machine inside of another. That whole process, translating one instruction set, Q code, into another, VAC-X assembler with an emulation layer in the middle, that sounds like a prototype for the JVM.
It was the industrial prototype, exactly. He saw firsthand the power of writing code for an abstract machine instead of a real one. But the sources confirm that this idea, this philosophy, it was a much deeper pattern for him. It went all the way back to his academic days at CMU.
This is the critical connection. So the impulse for virtualization was already there years before.
Years before. Back in his student days at CMU, he created a P-code virtual machine for the lab's DEC VAX computer.
So this was for a class, for a professor.
The goal was academic. His professor wanted to run programs that were written in a language called UCSD Pascal.
And why couldn't they just run the Pascal programs directly on the VAX?
Because UCSD Pascal was specifically designed to be portable. When you compiled a program in UCSD Pascal, it didn't generate VX machine code. It generated something called P-code portable code.
An intermediate language, just like Java's bytecode.
Exactly like it. And to run that P-code, you needed an interpreter, a virtual machine, running on the target hardware. So Gosling built that P-code VM for the VAX so that his professor and the lab could easily run programs written in this cross-platform academic language.
So the same core principle was tested in two totally different contexts. First in academia, to make teaching and research portable with P-code.
And then second, in industry, to solve a messy commercial porting problem with Q code.
And when you put those two historical dots together, you get the Java virtual machine.
That's the synthesis. It allowed him to articulate the ultimate goal for Java, achieving architecture-neutral execution for widely distributed programs. By hiding the hardware behind the JVM, and this is key, giving that JVM away with a permissive license, remembering the lesson from AWS.
He achieved the pervasive adoption he needed to define an entire era of computing. That layer of abstraction is why Java became the universal backbone for large, complex, distributed systems. The VM is really the whole story. Okay, so now the story takes a sharp turn. We're moving from this period of intense architectural creation to one of corporate transitions and, frankly, a lot of conflict.
A huge shift.
After 26 years at Sun Microsystems, a lifetime in tech, James Gosling leaves. April 2nd, 2010. And this happens right after Sun's massive acquisition by Oracle Corporation.
And this departure isn't just a footnote in a corporate history book. This is the moment where he goes from being the chief architect to being a very candid, very public industry critic.
He didn't just fade away. He was very clear about why he left.
Oh, extremely. He didn't issue one of those bland, sanitized press releases. Our sources detail the 4 specific reasons he gave for walking away from the technology he created and the company he built. And when you look at them together, they just paint this picture of a total breakdown of trust and culture.
So what were they? What were the 4 reasons that pushed him out the door after more than 2 decades?
He listed reductions in pay, reductions in status, reductions in his decision-making ability, and the real kicker, ethical challenges.
Ethical challenges. That's a strong phrase.
It's a very strong phrase. It really paints a picture of a culture changing overnight. It went from a place that valued long-term research and the intellectual freedom of its top engineers to a place focused on immediate cost-cutting and corporate control.
It sounds like the culture shock was just too much, moving from a company like Sun, which was very R&D driven, to a much more sales and lawyer-driven enterprise like Oracle.
He felt disempowered and, it seems, morally conflicted. And that tension, that underlying conflict between the old Sun engineers and the new Oracle management, it all came to a head in the famous Oracle v. Google lawsuit.
The lawsuit over Android's use of Java APIs. And Gosling's position in all of this was, well, it was really complex, almost paradoxical.
It was. He was caught between his loyalty to his creation and his clear aversion to his new employer.
Let's start with his view on the acquisition itself. He was pretty dismayed by the aggressive legal posture Oracle took right away, wasn't he?
He was highly critical. He gave this very memorable quote about the early integration meetings between the two companies. He said, and I'm quoting here, that during the integration meetings between Sun and Oracle, we could see the Oracle lawyers' eyes sparkle when they talked about Sun's patent situation.
Their eyes sparkle. That image just perfectly captures that shift from an engineering culture to a revenue through litigation culture.
It does. He clearly felt the acquisition was less about leveraging Sun's amazing technology and more about aggressively monetizing his portfolio of patents and copyrights. And that had to be the core of his ethical challenges.
And yet, when the legal fight with Google got going, specifically over whether Google's implementation of the Java APIs in Android was copyright infringement, he publicly sided with Oracle.
Which surprised everyone, given how he left and what he'd said.
He had to clarify it. He said explicitly, while I have differences with Oracle, in this case they are in the right, Google totally slimed Sun. So what was behind that? Why did he feel Google had slimed Sun?
This is so important to understand. His loyalty wasn't to Oracle's management, it was to the 26 years of work that he and his colleagues had poured into Java at Sun.
He was defending the work itself.
Yes. He said that many at Sun were disturbed by Google's actions. The feeling was essentially one of betrayal, that Google, instead of building their own platform from scratch or paying for a full license, had shortcut the process by just copying the architecture of the Java APIs. They were piggybacking on years of work and the entire ecosystem that Sun had painstakingly built.
So he was defending the intellectual property created by the original Sun team, no matter who legally owned it at that moment.
Precisely. But here's where his position gets so nuanced and I think so principled. He added a critical caveat later on regarding the court's final rulings in the case.
Right. He made a powerful philosophical point. He said he approved of the court's later ruling that APIs themselves should not be copyrightable.
And that's the true architect seeking, right? Despite his personal anger at how Google treated Sun, his long-term principles were aligned with the health of the entire software world. He understood that letting companies copyright basic interface specifications would just stifle innovation for everybody.
So he was prioritizing the future of computing over a single corporate victory.
It's an incredible display of intellectual integrity. He could support a specific claim that Google had slimed Sun while at the same time supporting the legal precedent that ensures open collaborative innovation can continue.
After this whole tumultuous period, he embarks on this really diverse post-Sun career. He doesn't just retire, he looks for new, hard problems.
His first move was interesting. He joins Google in March 2011. Maybe trying to find a better cultural fit, but he only stays for 6 months.
And then he makes a really fascinating choice. He follows a former colleague, Bill Voss, to a startup called Liquid Robotics.
Which is such a cool move. Liquid Robotics designed and built autonomous, ocean-going robots. Wave gliders.
That's a huge shift from enterprise software and server platforms.
But it's a perfect fit for a master systems architect. Autonomous robots require incredibly robust, complex, real-time distributed systems. They're operating in harsh, remote, unreliable environments. It was a chance for him to apply all his knowledge about concurrency and resilience to a physical system.
And Liquid Robotics was eventually acquired by Boeing in late 2016.
It was. And after that, he made his final big corporate move. In May 2017, he joins Amazon Web Services, AWS, as a distinguished engineer.
Which feels like a fitting capstone to his career.
It really does. AWS is, you could argue, the ultimate distributed computing environment on the planet. It's where global systems run at a scale that's almost impossible to comprehend.
So you have the architect of the Java virtual machine, the technology that enabled distributed computing for a generation, now working at the very heart of the world's largest cloud platform. It's his career coming full circle.
Exactly. He was designing for the ultimate realization of the networked architecture-neutral world that he helped create in the first place.
And even outside those big jobs, he stayed influential. He took on advisory and board roles. He advised Lightbend, the Scala company, which shows his interest in new languages for the JVM. He was a director at Jelastic, a hosting platform, a strategic advisor for Eucalyptus, an early private cloud company.
He never stopped engaging with these deep, foundational infrastructure problems, and not just in software. His board seat at Dirty Environmental Solutions shows he was thinking about how to apply systems thinking to all sorts of complex, real-world problems. So given the scale of his impact, it's no surprise that James Gosling has received the highest honors you can get, both from a civic standpoint and a technical one.
These awards really emphasize that his contribution wasn't just about programming. It was about building national and global infrastructure.
Let's start with the recognition from his home country, Canada. In 2007, he was named an Officer of the Order of Canada,
Which is Canada's second highest civilian honor.
It is. And to be named an officer, which is the second highest grade in the order, is reserved for people who've shown a lifetime of outstanding achievement and service to the nation. This isn't just a tech award, it's the country acknowledging that Java's global impact is a major Canadian contribution to computer science.
And his peers in the engineering and scientific communities have been just as clear. In 2015, he got the I.E. John von Neumann Medal.
The von Neumann Medal is for outstanding achievements in computer-related science and tech. It basically puts him in the same category as the giants who shaped the entire field. It recognizes seminal work that transforms the landscape.
And even before that, in 2004, he was elected a foreign member of the National Academy of Engineering, the NAE. The election citation itself is basically a perfect summary of his career's importance.
It's a great citation. It recognizes him for two things: the conception and development of the architecture for the Java programming language.
And for his contributions to windowing systems.
Right. It's a formal acknowledgement that the technical brilliance of New WS, even though it failed in the market, was still foundational work recognized at the absolute highest level.
And more recently, he was named a Computer History Museum Fellow in 2019.
That fellowship was awarded specifically for the conception, design, and implementation of the Java programming language. It leaves no doubt about his historical role. He was also made an ACM Fellow in 2013, got the Economist Innovation Award, and the Flame Award UCNX Lifetime Achievement Award, both way back in 2002.
The recognition across all these different institutions just proves Java wasn't just a market success. It was a true architectural triumph.
But his most tangible legacy, the thing he left for millions of developers, is his literary one, the foundational books that actually defined the language.
This is so important. For a technology to scale globally, it has to be documented perfectly. And Gosling was the principal author on the books that were basically the constitution for the entire Java ecosystem.
Let's touch on the two most important ones because they serve two very different purposes. First, there's the Java programming language, which he co-authored with Ken Arnold and David Holmes.
This is the user manual.
It's the instruction manual. It's the book that taught a generation of programmers how to use the language. The syntax, the libraries, the best practices. It ensured everyone learned Java in a standardized way.
But even more critical for that write once, run anywhere promise is the other one, the Java language specification. He co-authored this with other giants like Bill Joy and Guy Steele.
And the specification is not an instruction manual. It's the rule book. It's the legal technical constitution of Java. It defines with absolute precision how the compiler has to behave, how the bytecode must execute, what every single command means.
It's the document that technically and legally guarantees that a program compiled on one machine will behave identically on any other machine that follows the standard.
Without that specification, the write once, run anywhere promise just dissolves into total chaos. It's the anchor for the entire ecosystem.
It's the difference between a textbook and a legal code. And it shows how complete his legacy is. He didn't just invent the tech, he provided the documentary infrastructure for it to become a global standard.
And you can even see his interest in specialized systems in his co-authorship of the real-time specification for Java.
That's a fascinating corner of the Java world. Java, because of its garbage collection, was traditionally not great for real-time systems like factory robots or flight controls where timing has to be perfect.
And the RTSJ was an attempt to push Java into those high-stakes areas by defining ways to manage memory and concurrency with guaranteed predictable timing. It just shows that even after defining the standard for general computing, he was still trying to solve the next hardest problem. It's just a completely comprehensive body of work. Hashtag tag outro.
So when we step back, what does this all mean? We've traced this incredible journey from a kid in high school analyzing ISIS-2 satellite data, which demanded robustness from day one,
all the way to his architectural genius in creating the Java virtual machine and standardizing this idea of architecture-neutral execution.
He took these niche ideas from academic research, like P-code for UCSD Pascal, and he successfully scaled them to define how programs run across the entire planet.
Yeah, the software we all rely on today, whether it's running a massive data center at AWS or a complex financial trading system, or even the early foundations of the mobile web. It all rests directly on the principles of virtualization and rule-based design that he established back in the 80s and 90s.
He created one of the most successful commercial technologies ever. He stayed with Sun for 26 years, literally defining the company and the language.
And yet, maybe the most telling part of his whole story isn't what he created, but why he left. The source material shows this consistent pattern, his walkout from Oracle, citing ethics and a loss of control.
And then his choices after that, to work on really hard, high-impact problems at places like Liquid Robotics or AWS.
I mean, imagine spending more than 2 decades building a company's flagship product, only to walk away because of a moral conflict. It just speaks volumes about his priorities. It was always principle and intellectual freedom over just sticking with a corporate legacy.
It seems like for an architect whose real passion was solving these deep, complex problems of how code runs everywhere. The aggressive corporate machine that grew up around his invention eventually became an ethical barrier he just couldn't accept.
The sources show he always prioritized engineering integrity. When he felt his creation was being misused, like with Google and Android, he defended the original work. But when his new employer, Oracle, tried to use copyright law to strangle future innovation,
He spoke out against them. He prioritized the health of the whole ecosystem.
it did.
And that leaves us with a final provocative thought for you to think about. Despite creating a technology that became a pillar of global commerce, James Gosling ultimately chose to walk away from his creation's corporate home to stay true to his principles of engineering freedom. So does the greatest innovation sometimes require the innovator to prioritize those philosophical principles over decades of corporate dedication, even if it means cutting ties with the very thing they built? It's a profound question about where the true value really lies, in the structure of the code or in the ethical environment where that code is allowed to grow and thrive.